Naming acids. Acids are molecular compounds that form ions when dissolved in water. So when we're naming things as acids, they're always dissolved in water. The way we're going to recognize acids in this class is that hydrogen is the first element. So anything that starts with hydrogen is an acid. And the acids are divided into two groups: binary acids, which are hydrogen and a nonmetal, and oxy acids, which have hydrogen, a nonmetal, and oxygen. And so there's the breakdown. We recognize them by their first element being H, and there's two groups. You get hydrogen and a nonmetal, or hydrogen, a nonmetal, and oxygen. And there's different names for both kinds. So the binary acids first. So binary again, meaning two, exactly two nonmetals, hydrogen and something else. And so the name follows this pattern. We're going to use the prefix hydro. We're going to take whatever that nonmetal is, the name of that nonmetal element, and we're going to change the end of its name to ic, and then we're going to throw the word acid on the end. So all acids have the word acid in their name. So here are some examples. HCl, and in parentheses, the AQ here just means that this is dissolved in water, and so we name it as an acid. Your book uses that convention, and it's correct, but I'm not going to get hung up on it. So HCl is hydrochloric acid. Two elements, hydrogen and chlorine. The hydrogen tells us this is an acid. Then there's chlorine. So we put hydro in front of chlorine, and we change its ending to ic, hydrochloric acid. HBr is hydrobromic acid. Now if we have HCl in the gas phase, not aqueous, that's actually a binary molecular compound, and it would be hydrogen chloride or hydrogen monochloride. But again, I'm telling you that just so that you won't be confused if you see it sometimes called hydrogen chloride instead. There is that very subtle difference, but we're not going to worry too much about it. So let's look at this one, H2S, aqueous. So we have two elements. The first one's hydrogen, and the second one's sulfur. Two elements, binary acid, hydro-something-ic acid. Well, this has sulfur, hydrosulfuric acid. Does that make sense?
So since there's two on the hydrogen, it wouldn't matter?
No.
Okay.
And that's a good question. Why is there a 2 on the hydrogen? Well, acids are not actually ionic compounds, but when you put them into water, they form ions. So what ion does sulfur form? What charge does it have? 2 minus. And what charge does a hydrogen ion have? +1. So in order for those charges to balance, we need 2 H pluses, and that's why the formula is H2. So let's name these guys. HF. We had 2 elements. Darn it. You don't know what funny little words you use until your 2-year-old child starts saying darn it all the time. And yeah, and shoot and darn. There are worse things. And my parents were visiting once. I'm just arguing with my iPad right now. My parents were visiting once when one of my kids was at that age and was saying shoot and darn for everything. And I was like, kind of embarrassed. And my mom says, oh, don't worry about it. You got shoot from me and darn from your father. I'm like, oh, it's your fault. Okay, great. Okay, I'm sorry about that. HF, 2 elements, right? Hydrogen, and fluorine, 2 elements. So fluorine, fluor. So fluoric, this is binary, so it's hydrofluoric acid. The name comes from the element and follows a pattern. How about H2SE? 2 elements, right? No oxygen, just 2 elements. So Se is what? Selenium. So selenic, and it's 2 elements, so we're going to put hydro on the front. Hydroselenic acid. Don't run across that one too much, but it's there. Any questions? There are not very many of the binary acids. There's like a gazillion ionic compounds, and there's like half a gazillion molecular compounds. And these binary acids, there's just a handful of them. But then there's the oxy acids. The oxy acids have oxygen in them. And so when we look at the oxy acids, like HNO3, there's the hydrogen, and the rest of it is nitrate. All of these oxy acids have an oxy anion in them. H2SO3 has sulfite. H2SO4 has sulfate. The names of the oxy acids come from the names of the oxy anions. And the number of hydrogen ions is related to the charge. So here, sulfate, come on, cooperate here. Sulfate is 2 minus. So then in the formula for the acid, it's H2. There's another acid based on phosphate. How many hydrogens would that have? What's the charge on phosphate? 3. So it needs 3 hydrogens. H3PO4. So that's got phosphate in it. So the names are related to the charges. I'm sorry, the names of the acid is related to the name of the anion. Yeah, so I don't find this slide to be particularly helpful, but here it is anyway. So when we look at those oxyanions, there's 2 endings. There's ite, which could be like chlorite or hypochlorite, and there's ate, like chlorate and perchlorate. So all the oxyanions either end in ite or ate. So we look at the ending on the name, and then we change the name to make the acid. And how do we remember this? Well, I've got a silly sentence for this one too. Rick ate him before he could bite us. Is that silly enough? Okay, so ick and ate go together, ite and us go together. If the oxyanion that's present in that acid ends in ite, then you change the name to us. So nitrite becomes nitrous acid. If it's an ate, like sulfate, then you change it to ick, and you get sulfuric acid. Yeah. So Rick ate him before he could bite us. So here's a table of some of the common oxy acids and the anions that are present. So like here we've got HNO2. Well, if you cover up the H, what's left? NO2. So what's the name of that? Well, I know the name of NO3 is nitrate. This is the light version, it's nitrite. So that's nitrite. Sorry, I can't point here. Nitrite. Ite us, bite us. So nitrite becomes nitrous acid. Here's H2SO4. Cover up the H's. What's left? SO4, that's an oxyanion. It has a special name, sulfate. RIC8, IC8, sulfate, sulfuric. Now, yes, the UR just, oops. The UR just kind of popped back in there. Why? Again, I don't really have a satisfactory answer for that, except that maybe it sounds better than sulfic acid. Come on. So the UR goes back in there, so sulfate becomes sulfuric. Acetate becomes acetic. You change the 8 for ic. Do you see the pattern there? And again, there's not that many of the oxy acids either, but they all follow the same pattern. So if it's a binary acid, 2 elements, then it's hydrosomething-ic acid. If there's oxygen, you do not use the prefix hydro. So let's just look real quick at a couple of examples. Now here are HCl and HClO. Well, actually, let's do HClO3. That proves my point a little better. So one of these is chloric acid, and one is hydrochloric acid. And it matters. So which one is hydrochloric acid? The top one. 2 elements. Hydrogen and chlorine, hydrochloric acid. The oxy acid is the chloric acid. So this prefix hydro is only for the binary acids, 2 elements. And again, it's just going to take some practice to learn those. Okay, so here's a couple of examples for us to practice on. HNO2. Well, the hydrogen tells us it's an acid. So let's look at what's left. What's over here? What's the name of that? Nitrite. So this is the nitrite ion. We're going to take the ite off. And which suffix goes with ite? Us. Bite us. Okay, so nitrite becomes nitrous acid. Nitrous acid. How about HClO4? There's hydrogen. So there's hydrogen over there, that makes it an acid, and over here we have ClO4. That's related to chlorate. Chlorate was ClO3. This has more oxygen. This is the hyper version. This is perchlorate. Here's that suffix 8. Which goes with 8, ic or us? Ic. So this becomes perchloric acid. So there are specific patterns, and then we follow the patterns. Any questions? Nomenclature is a topic that students tend to have trouble with. And I think just because there's all these little things you have to remember, but it's like learning to play a somewhat complicated game. You know, it says for ages 8 and up, right? And you're like, gosh, I'm 22 or however old you are, I should be able to play this. Yeah, well, it takes a little practice. You don't just, I helped my 5-year-old learn how to ride a 2-wheeler last week. You don't just hop on a 2-wheeler and go. And even harder than that is learning how to ride a ripstick. Have you ever tried one of those? Those are hard. I've helped a couple of my kids do that. It's painful. You don't just hop on and start riding. But why do they keep trying and trying? Because they think the reward is worth the effort. So what's your reward for learning nomenclature? Well, it's not necessarily going to be a warm, fuzzy feeling. It's not necessarily going to be that you're just going to really enjoy naming compounds. But why are you going to school in the first place? You have some goal in mind, right? And somebody told you that you have to take this class, right? So this is a stepping stone towards that ultimate goal. And it's going to take some work. And maybe you think, well, this is really dumb. Why do I need to know this? Well, some people who are fairly important think you need to know this stuff. So just put some work in. It's like riding a ripstick, learning a new board game. It just involves some practice. And sometimes you fall down and you scrape your knees. The good thing about this is you won't have any physical damage from learning nomenclature. Unless you start pulling your hair out, but I wouldn't recommend that. Oh, and I digress. And here's a table, really more of a flow chart, showing just kind of a schematic of all these things that we've been talking about. So here are the ionic compounds. Ionic compounds we identify because they've got a metal and a nonmetal. And we've got two groups here. The metal forming only one kind of ion. That's metals in group 1A, 2A, 3A, or zinc or silver ions. And then their names, I hate it when I do that, I pointed at the wrong half of my screen. Then their names are just the name of the metal, name of the anion, with its ending changed to "ide." Or we can have any other metal that's not in one of those groups. Then we have to use a Roman numeral to indicate the charge. Okay, when we're naming it, we find that charge based on the charge of the anion. Then we talked about the molecular compounds, only nonmetals. And this is where we use numerical prefixes to tell how many of each element. So the example P2O5, P2 is diphosphorus and pentaoxide. So diphosphorus, pentoxide, I've heard it both ways. And then we've got the acids that we just talked about. The binary where you've got two elements, so you use hydro, whatever the other element name is, change the ending to ic in the word acid. Or we've got the Oxy Assets, and there you're looking at what oxyanion is present in there. Is it nitrite? Well, then you'll take the ite and change the ending to us. If it's nitrate, you would change the ending to ic. So this is kind of a good guideline, a thing when you're now going to try to do the homework and name all these different kinds of compounds. This can help you sort of retain the big picture. Resist the temptation to use these prefixes for everything. Okay? Something like this, FeCl3, a common student mistake would be to call that iron trichloride. Well, maybe I might know what you mean, but it's wrong. And this is not calcium diiodide. And we can't call this dihydrogen sulfur trioxide. Very creative. I know you like the prefixes, but you can only use them for two nonmetals. Another way to do, use this if it's helpful to you or not. So the idea here is they're kind of talking you through the flowchart. So first you have to identify what kind of a compound it is, and then you just go down to things. And I'm not going to talk about